just about ready to start.
Yep, I'm ready.
Okay, good evening, everybody. My name is Colin Pullum. I'm head of the School of Chemistry, and I'd like to offer you a very warm welcome on this cold winter's night to this inaugural lecture by Professor Michael Seery. I'm actually not going to introduce him. I shall say some words at the end, but I'm going to introduce the head of college, Professor Dave Robertson, who's going to introduce Michael, ready for his lecture. Dave.
Thanks, Colin, and thanks.
I knew I'd forgotten something, right? And nobody reminded me, right? Fire, right? So you are in a chemistry department. Chemistry departments do have a habit of sometimes having fires. There are no fire alarms scheduled for this evening. So if you do hear the alarm, please leave by this door or the door behind, and we assemble at the David Brewster statue, okay? So hopefully there will be no incidents. Now I'll let you talk, Dave.
So now we're all safe. Welcome everybody, and especially welcome to, I see a serried rank of family and friends as well as the academics here. So thanks for coming. These are special occasions, and for the chemists in the audience. I mean, of course we got brilliant education in various different schools in science and engineering. But as a school, chemistry is usually a place where people go, oh, they'll know how to do this when it comes to education. It is a kind of characteristic of chemistry, if you hadn't noticed it before. So you do have that reputation. And my role is just to say a few biographical details, but maybe one personal comment at the end, because I'm allowed that. So the thing about education is Michael's a professor of chemistry education. He's also a director of teaching, I believe, in chemistry. So you're part of the reputation that you've got. And his research explores learning in laboratories and supporting students' independent learning. He's editor-in-chief of the Royal Society of Chemistry Journal, Chemistry Education, Research and Practice, and a member of the RSC Education Division Council. And he's received several awards for his work in education, actually a lot of them, including the RSC Higher Education Teaching Award, the Irish Learning Technology Association Jennifer Burke Award, and the Irish National Academy for Integration of Research, Teaching and Learning, Teaching Excellence Award, which is really hard to say in one go, as well as an RSC Inspirational Member Award for his work in diversity and inclusion activities for the Society. So that's as far as I'll go in the bio, although there is a lot more that I could say. But I like to show I've done my research for these. So looking on Twitter, in a recent tweet, Michael says, quotes, you can check this up, by the way, if you want to look, quotes, writing my inaugural lecture. Challenges come down to distilling life's work into a few accessible headlines while hunting down embarrassing childhood photos. So I'm looking forward to a riveting talk, Michael, with lots of embarrassment. Take it away. Good luck.
All right, so thank you, Dave, for that introduction and embarrassing biography. And thank you, everybody, for coming. I'm just thrilled that there are so many people here from the school and from the university, and obviously, yes, sorry, let me just, this one problem I have is voice projection. So let me, is that better? I'll just sort of talk this way. I'm just really thrilled that so many people have come. And I also see some students in the audience, which is simultaneously fantastic and frightening, because it gives students lectures on how to present for their final year projects. So all I'll say to the students in the audience is, for the next hour, do as I say and not as I do. And what I want to talk about, welcome, what I want to talk about is work that I've been doing here at Edinburgh really over the last 5 years around student learning, and especially supporting student learning, really trying to foster independence in student learning. So there's three parts to my talk, so you'll know how, as we're progressing through, that we're getting closer and closer to wine at the end, which is the most important part of the evening. And in the first part, I want to talk about the main part of my work, really, which is around learning in the lab. And in this painting that I'm using to illustrate this first part of the talk, we see a very old 17th century painting of essentially a chemist, an alchemist. And in this painting, we have this alchemist, and he's working hard away using chemical kit. So there's this sense that even in paintings as old as this, that a chemist or somebody involved in chemistry is implicitly associated with chemical kit or doing chemistry techniques. And in this painting, I haven't looked up what the interpretation is, but I'm guessing that this lady in this beautiful gold dress is the modern day equivalent of the funding agency coming to see whether the chemist has managed to turn lead into gold, and she doesn't look very happy. So I don't think he has. All right. So I want to talk a little bit about learning in the chemistry lab. Obviously, this is important not just for alchemical history reasons, but if you look up some of the amazing work that my colleagues do, and I've just picked 4 here that all work in this building, they're all publishing and producing work that relies on an implicit knowledge of chemistry and how to use chemistry in practice. So the people working here have to know how to do chemistry techniques, and I include computational chemistry, obviously, know how to use their chemistry and apply it. So I can't tell you much about this chemistry, unfortunately, anymore, but what I am interested in is how did the people who work with these people, eventually, there are students and people who go to industry and people who get chemistry degrees, how do they learn how to do chemistry? And that's what I've been focusing on and thinking about for a long time. All right, so the first thing is to think back, pare it right back. Why do we have teaching labs in the first place? Why do we need this very expensive resource where we are getting out teaching labs and paying lots of people to teach students this practical work? And in a way, we can distinguish knowledge that we teach into 2 forms. The first is what's called substantive knowledge, or the substance of a discipline. So if you imagine a musician may know a very high level of music theory. They'll understand, I don't know anything about music, so I'll have to try and pretend I do, but they'll understand dynamic and motion and scales and all that kind of thing that musicians know about. So this is what we call the substantive knowledge, the substance of the discipline. So in chemistry, obviously, there will be theories and laws and things that underpin the discipline of chemistry. But then if the musician is going to play, they need to understand how to take all of this information and actually apply it in practice. And we call this syntactical knowledge. In other words, putting this knowledge together in syntax and actually using it in application. So the core reason for thinking about laboratory teaching is this core distinction of laboratories are a place where we can think about this syntactical knowledge, thinking about teaching students how to take what they know and apply it in practice. So as you will learn, I'm an historian. And from a history point of view, this is really interesting. So when you come into the front foyer here in Joseph Black Building, you'll see on the back wall stone plaques of all the professors. And on the far left are the chairs of chemistry. So this is essentially the university's commitment to teaching chemistry here. And as you can see, we're a very old chemistry department, going back to 1713. But I want to tell you about this guy, Thomas Hope, because Thomas Hope is chair of chemistry at a time when people are really thinking about laboratory education and integrating laboratory education into the chemistry curriculum. So Hope, like every professor at the time, worked on a basis of pay-per-view. So the more people that attended his lectures, the more he got paid. So I would be making a fortune tonight. And so here's just a random student I happened to pick up called Charles Darwin. So Charles Darwin attended Hope's lectures, studied chemistry here, and he would have been one of the people contributing to Hope's money. And Hope was the richest Scottish professor in the 1820s. He was a very successful lecturer, very good at, he created lots of very enthusiastic and engaging demonstrations, very good at teaching chemistry, and made a lot of money out of it. And Hope was completely opposed to the idea that chemistry students should learn how to do practical work. That was a role subservient to the nature and discipline of chemistry, and that was a role for supporting people who would support chemists. But at the time, in the 1820s and 1830s, there was a shift towards people really wanting to be able to learn how to do chemistry. There was a rise in agricultural science and industrial science, as well as the core role of chemistry at the time, which was a medicinal chemistry. And so lots of labs began to be set up around the city, and Hope eventually had to relinquish, but he was really against this. So the culture at the time in Edinburgh, and indeed the UK, was that chemistry labs weren't really part of the curriculum. And this led to this rather scathing comment at the end of Hope's tenure, which said, there is a great deal of chemical knowledge in Scotland, but there are very few chemists. And I think this is really getting at this issue of syntactical and substantive knowledge. We may know something, but do we know how to use it? All right. So what happened then was people stopped going to university here in the UK and migrated to the continent, where new schools of chemistry were emerging. And one of the most famous schools was Justus von Liebig's lab in Gießen in Germany. So here's a picture of von Liebig. Von Liebig was also very good at making money. This is his precursor to oxocubes. So here's me in Gießen recreating this scene, dressed as well as those people are. And in von Liebig's lab, he had this a core part of the teaching day was lab classes. And von Liebig was essentially the academic forefather to lots of very famous and eminent chemists. So this idea of chemistry laboratory work being a core part of the curriculum was embedded from that time. You can see also that all the students went to go to bed, so I think we could perhaps put that in our timetabling system. So Edinburgh did catch up, so after Hope's time, Gregory and especially Playfair started to integrate practical work into our curriculum, and our first-year teaching labs here are called the Playfair labs. All right, sadly that's the end of the history bit for the moment. All right, so what is it like to be a chemistry student doing practical work? So in general terms, we tend to ask students to look at something before they come, even if it's just read the manual. Sometimes we give them some work to do beforehand, and then they come into their lab class. So our students would do 3 hours in first year, 6 hours in second year, and 12 hours in the third year. They do a lot of practical work, and they make things or measure things or study some chemical reaction or something to do with the chemistry. And then afterwards we go away and we ask them to take the results that they got from that, put it in a report and situate it into what's generally known, and they sort of learn what their results mean on that basis. So on paper this is a very practical, very sensible arrangement, but in practice, in modern education and mass education, we now assess this activity, this whole approach, primarily by the post-practical activity. So therefore, in students' minds, the effort and the intellectual basis of what they have to do is on the latter part of this, on the post-practical activity. And this isn't to blame students, they are just playing the system that we have set up. And this is a huge problem. This is a well-documented problem in the chemistry education literature. So going back nearly 40 years, Alex Johnston, who is a professor of science education in Glasgow, wrote that it is not uncommon in undergraduate labs to see students working as fast as possible just to get finished with little or no thought about what they were doing. And more recently, Marcy Towns and her student Britland de Corver wrote, for a research-intensive university, even students who profess an intrinsic love of chemistry and chemistry labs do not have sufficient motivation to carry out the experiment in a deliberate and attentive manner, nor do they have adequate reflection skills to realise that they are failing to meet their own learning goals. This is really tragic. I just think this is really something that resonates certainly a lot with chemistry educators around the world, and something that really struck me for a discipline where practical work and teaching practical work is so implicit in what we do that something is going so wrong. So I've been thinking about practical work for a long time, but when I moved to Edinburgh, I thought this was the nut that I was going to crack. This is the challenge that I was going to take on. All right, so for my final year students, take a drink if you feel your mouth's getting a little bit dry. All right, so what this meant in practice was, so let's stop focusing on the report. Let's put our effort into getting students to intellectually engage as they are doing lab work. So a student, when they are doing lab work, should have a sense of what they're doing. It seems simple. And for that to happen, we really need to think about how do we prepare them for that in lab work. So when I am in a lab and I am doing an experiment, I have something intellectually to lean on. I understand the general basis of what it is I'm doing. Right, so when we try and design educational approaches, generally, we tend to rely on what are called frameworks. So rather than me just saying, I think this is a good idea, we should do it this way, we tend to try and take some framework that is based on psychological evidence or educational evidence or even sometimes philosophical evidence, and use that as a sort of a template to guide what it is we do. And this means then that whenever we try and think about what we're going to do or whether we should do something or not, we tend to use this as this framework as a way of thinking about, as a way of helping us answer those questions. And the problem with the lab education literature, really going back over the last century, is that everybody is doing good things that sometimes work, sometimes don't, but the problem is that there's no real kind of guiding principle to it. So it's very hard to say why something is having some impact. So I was reading around a lot, looking for a framework that would match a lab education setting, and came across one called the Complex Learning Framework. And this describes a complex learning situation, any situation being complex if it fulfills these three criteria: integrating knowledge, skills, and attitudes, definitely happens in the lab; coordinating qualitatively different constituent skills, so being able to do lots of different things at once; and applying what is known to real settings. So this really hit home to me as something that described the lab environment very well. The advantage of using a framework is that it spits out ideas and suggestions as to what we should do in terms of things like supporting learners in that framework. So what we're obsessed about in lab education is information and where students get information from. So the Complex Learning Framework describes in very general terms what information students should have in advance. So this is what's called supportive information. This is a kind of a conceptual basis, not necessarily the nitty-gritty chemistry, but a general conceptual understanding of what's going on, and also why a particular experimental approach or why a particular experimental technique might be useful, why it is telling the student something that they would know. So avoiding what's called black box syndrome, where students are just using something or doing something, but they don't really understand what's going on. And procedural information is essentially what you could just get on the fly. So you're working in the lab, you're doing something, oh, press that button there. It's just general stuff that can be just picked up as you go along. And the second part is more interesting and talks really ultimately about how we can develop a curriculum in lab education. So I've perhaps oversimplified it here, but it talks about simple to complex sequencing. In other words, we should start off easy and make things progressively harder. Sort of very obvious statement. But slightly more involved is, so imagine you're learning to drive a car. You wouldn't spend one lesson on using the clutch and one lesson on the gear stick and one lesson on the steering wheel and then send the student off and off you go and drive. Obviously, it's about learning how to do all these things at once. So in a curriculum design point of view, we have to think about presenting the whole task to students and incrementally making it more and more difficult. So really, from my point of view, the complex learning framework really spits out how do we support learners in terms of information they need in a complex situation, and how do we design a curriculum. So this is our learner, and in terms of supporting their information, Alex Johnson's paper that I mentioned earlier very neatly summarised all of the things that are going on from a student point of view in terms of information. They are being bombarded with lots and lots of information in a laboratory setting. And Johnson wrote, and Johnson is an extremely experienced educational researcher, wrote that it's no wonder that students can't intellectually engage in what's going on, because they know the report is at the end and that's their goal, and all they have to do is intellectually sort of skate across the surface, not really able to engage with the material. And this is due to something called working memory capacity. Learners, and all of us, have a capacity for a certain amount of information that we can process, but not more. So if you're in a situation where you're being overwhelmed, it's very hard to engage with that material intellectually. So what we can do is we can provide some of this information in advance. So the complex learning framework is giving us guidelines as to what supportive information we can provide in advance. This is very easy nowadays. It's very easy to whip up the YouTube videos. So these will provide students with videos or guidance documents that really set the scene and are designed from the supportive information point of view. This is about this intellectual basis. This something students can lean on intellectually when they're doing their lab. So I make videos and that kind of thing to support lab work. And I decided a long time ago to put anything I made for education purposes freely available so that anybody can, in the world can use them. So I have a YouTube channel and it's now over 850,000 views, so it's very gratifying. This does mean, though, you expose yourself to the very weird and wacky world of YouTube comments. So I've done some thematic analysis of the comments that I've received. The first one, as you may gather, of a slightly unusual accent. So the first one comments sort of. So I've been. People think I'm South African, German, worryingly Austrian. Thankfully, somebody recognises my true accent. Different ways of saying thank you, so very polite thank yous from Peru and India. After reading the last one, I couldn't understand this, so I went to the Urban Dictionary, and apparently dank is a good thing now, so we're down with the kids. And then sort of more extreme forms of thank you, which we all have fragile egos. I'll take it. All right, so that's the support, that's the information support side of things. The second thing is much harder, obviously. We want to design a curriculum so that students, when they graduate from Edinburgh, leave with what? What do we want? We want students that are independent, that can solve problems, that can work in messy situations, that can try things out, fail and try again. Just students that are able to adapt and be resilient to what we call experimental design. And this isn't only necessary for chemistry, this is necessary for everyday life and any career. So this is why chemistry graduates are so employable. They have this fantastic range of skills. And when we think about curriculum design, so we have our school pupil coming in and we have our chemistry graduate leaving. When we think about curriculum design, we want to think about what is the journey these people are going to go on, how are we going to structure it. And things like accrediting bodies and the Scottish Qualifications Framework give us some sense of what should be happening in each year. But really, us here in the school have a very strong voice about what it is we want this graduate to be. So I've kind of given you some attributes of that graduate. So we've been through this massive transformation program over the last few years, a project much bigger than me, and I acknowledge that at the end. And we've been restructuring our program. And now, for example, our Year 5 students, so students spend 5 years in Edinburgh doing an MChem, a Master's in Chemistry. They spend their final year now doing a full year-long research project, either here in Edinburgh or in industry or abroad. I mean, this is just such a fantastic opportunity for students. And when you talk to these students, you hear from them the experience they're gaining, the independence they're developing. It's just amazing. But for students to get here, we need to think about, well, what is the process for supporting them year on year? The complex learning framework says, simple to complex, whole task. So we need to be thinking about how does this progress each year? So this means backfilling down each year and having a particular emphasis in each year to get the students to that stage. So our Year 4 students can leave at a bachelor's level, so at that stage they will also be having to think about experimental design and so on. For MChem students, we have built in a new Year 4 course at great cost, really, because we had to build a new lab for this. This is a massive investment from the school and from industrial partners, showing the value and importance of developing students' research skills. So this now is the bridge between the first three years of formal teaching labs and this 5th year. But the purpose of this year is really to give students a playground to really start learning about unfamiliar experimentation. It's quite difficult for them, but this is really to make the jump before they go into Year 5. Similarly, Year 3 into Year 4, we really need to start structuring their experimental design skills and so on, building models and just learning how to do chemical techniques. And the idea from the complex learning framework is that each of these run through every year, but every year adds on some new iteration. That's the new focus for that year. So what I thought I'd talk about is just two examples of what this looks like in practice. So in thinking about experimental skills and competencies, what we want to be able to teach students is experimental technique. So when you go into a lab and you do an experiment, how do you know what to do? So we all watch Bake Off, don't lie. Even Dave watches Bake Off. And when you do the technical challenge, the reason the technical challenge is so difficult is because you haven't got a clue what you're doing. So if you're in a lab and you have to do some chemical procedure, how do you won't know what to do because you won't have had some insight of the process. So we have a model where students will watch videos that describe this process. I learned a lot of chemical techniques doing this project. And then we bring them into the lab, and in first year we have a setup where the students will actually video each other doing these techniques, and then they'll be able to review it. They have a video on their phone of them doing this technique. They can make it better if they like, and then they submit it for assessment. And this meant having to develop lots of videos to support this. So I worked with this group of people. So we're very lucky here with amazing PhD students who love to get involved in teaching activities. So Hendra was my own student, but Ewan and Helen and Amy, sadly for me now, all graduated, were fantastic. They were principal career development scholars, and they got involved in supervising Maciej, who was an undergraduate student but is now a PhD student in the Lloyd Jones group. Maciej made lots of videos to support this approach. So we now have this bank of resources that we can give to our students. Maciej was fantastic, especially if he was here. He was fantastic, especially because he came from a chemistry Olympiad background. So of all of us, he was the one who knew how to do these techniques. So this is fantastic. This is a great model of teaching experimental competency, so much so that actually I do a lot of work with a school teacher and look at trying to bring this model into secondary school education. And I should say, Naomi does a lot of work, and I sort of look at her doing it. But Naomi Henna from Northampton does a lot of work now in this exemplar try it out yourself model in school education. It's not just about basic glassware technique. We tried this out with second years and more advanced techniques. And here's a student using UV vis spectrometer, which is a standard piece of kit. And the student here, we're bringing up the level a little bit. The student has to explain what the experiment, the technique is, explain how it works, how it's generating, in this case, a signal, how you actually use it, and then how you extract the information at the end. So giving a full overview of what this technique is. And this is with Thomas Lambert, who's in Dave Clark's group. All right, so the second example of two that I want to share about curriculum design is this step here, this experimental design step. Because I've drawn it as nice, neat steps, but if you ask any student in the audience, third year is really tough. This experimental design is really, really tough to learn. And chemists will understand this shape, but it's quite a barrier to get from the quite secure environment where we really structure students' approach in second year to a slightly more Wild West approach in third year, where we want them to start thinking about planning and designing experiments. So we moved away from a model where we just sort of essentially moved from this kind of approach to an unfamiliar approach. We really had to try and structure students' understanding of what it means to design an experiment. So again, the Complex Learning Framework offers guidance. So we have a setup now that where students come into third year labs in one of our sections, and they will do pre-lab preparation, because as everybody in this room now knows, you would be insane to have a lab experiment and not have pre-lab preparation. That is my core message that I want you to take away from. Pre-lab is a must. And the students would do an experiment pretty much as they've done before. So it's pretty highly scripted, and they'll run through the experiment. But in this, we want them to build up a rapport with demonstrators. So we've built in structured time where they have to talk to demonstrators and talk about their experiment. They're building familiarity with the technique, and they're getting a sense of what this approach actually spits out. So they're building up this profile of what this experiment is about. Now, in second year, we'd say, OK, that's great, move on to the next experiment. In third year, we're focusing on experimental design. So the students now have familiarity with all of these things. So what we do in the second step is, instead of sending them on to another experiment, we give them the same experiment again effectively, except different conditions or something extra that they have to find. So basically, we give them a problem. And they have to use all these bits that they've learned in the first part, so they're familiar with techniques, they understand the kind of outputs that they can use, and they're able to use this much more coherently and much more intelligently, I think, to work through the experiment. And then they emerge as a competent chemist. So they go through this sort of cycle 3 times in third year, and I think this was really giving them a lot of exposure to experimental design skills. So again, I worked with amazing PhD students from other groups in this, so Ariana and Will were both demonstrators in this lab, and they saw the capacity and potential to really think about teaching developments and teaching experimental design in labs, and they were just amazing. And Thomas Mine, again, was an undergraduate intern. Undergraduate interns are fantastic. He did all that. We said what we wanted, and he made it all happen. Okay, so what I've tried to show you is that if we can think about focus on learning in the lab, we can start to get a sense of intellectual engagement in the lab. And as we roll this out, we could hear from students in terms of feedback. We could hear from colleagues who are supervising in the lab. We got a sense that this was going reasonably well. But I'm an education researcher, so a parallel thing on all of this was to actually look under the bonnet and find out what's going on. So I had 2 PhD students working on this, and the first student was Hendra, who is now graduated, again, from me, sadly for me. He's now postdocing in Copenhagen. And Hendra was interested in 2 things. The first was this idea of information management. So Johnson said ages ago, information overload is a big problem. So how, in this new setup, is information being processed? So Hendra interviewed lots of students and tried to extract from them their sense of information processing, information management, how these labs are going generally, what their experience was in the lab, and come up with several themes, but 3 of which I'll share. The first is pretty obvious. Students love the idea of having pre-labs, being able to develop this competency and knowledge in what it is they were going to do. Perhaps something we weren't expecting was that these videos that we were preparing, these resources that we were making, were essentially setting the expectations a little bit higher. Students understood as when they were entering into this environment that there was something more demanding of them. The second was key for me. So if we want intellectual engagement in the lab, which is the core problem that I've mentioned with lab education, I wanted to hear students talking about this. I wanted to hear students talking about giving us signals that they were actually thinking about things while they were in the lab. And we got lots and lots of that. Students reporting that they were documenting, recording, describing, processing, thinking, planning, lots and lots of stuff saying, I am in the lab and I am actually thinking about what I'm doing when I'm here. And the third theme was quite surprising and very nice. And this was students talking about this emerging sense of being a prototype scientist. This sense of, I understand that I'm developing here experimental design skills. I understand now that I'm actually getting some taste of the experimental process, the design process. And they really enjoyed that. There was lots of stuff about feeling accomplished or feeling a sense of value about what they were doing, which is very powerful. And when we got these kind of signals, Hendrik went back and interviewed lots more students to get a sense from them, how much do you really understand what this is? So we did a second round where we looked at what we call nature of science, which very briefly is a kind of a sense of, do you understand how the scientific process works? Do you understand if you do an experiment, what the kind of output you get from that means, how much credit we can give it? And he interviewed students and gave them case studies and questions and really tried to tease out from them their understanding of science. And then we binned those categories and tried to get a sense of what was their general perception. And we found overall there was a mixture. As you might expect, about halfway through the first go at experimental design, we were getting a mixture of naive, what we call naive, transitional and informed views of nature of science. But one thing that was clear, and a kind of a very clear signal for us from Hendrik's work, is that if we think we are teaching students experimental design skills, we've got to tell them we are teaching experimental design skills. So a very easy win for us was just to really, not just to bring them through this process, but really explain and elicit to them that they're learning these skills. A slightly more involved project is by Zinchi, who is here somewhere. And Zinchi is an educationist, so she comes from Morehouse School of Education, and she's coming in and exploring this weird and wacky world that is a chemistry department. And she's coming in and really interested in thinking and finding out what's going on for students in terms of their needs in a learning environment. So us as academics, we might look at a student and go first or 2-1 or whatever, we would have some shell view of that student. For some reason I've drawn this as an egg, I'm not really quite sure why, but if we crack open the egg, what Zinchi is finding when she interviews students is, yes, of course they have needs to develop knowledge and resources and want to know what it is they're doing. They want this. You know, these are third-year students. It counts towards the degree. These are very keen, very involved, very motivated students. Needs and desires in terms of wanting to say, okay, I'm learning something from this and I want to know how to apply this to different situations. And then bigger issues around identity and this emerging sense of I'm learning how to be a chemist here. Or if the student, Zinchi also talked about career aspirations, if the student didn't want to be a chemist, because a chemist obviously is a very translatable degree, but they had other career aspirations in mind, were they aware of the skills or they had a desire to learn the skills, what skills they were gaining as a result of these activities? And again, a message from this is we need to be more explicit for students about the skills that they are developing. Okay, so I think what I've tried to show you is that this process is, I think, really working. It's very hard for me to say that personally, so I'll just become director of teaching for a moment. Okay, I'm now director of teaching. This is amazing. Edinburgh students are amazing. They're learning such fantastic experimental design skills. They're emerging. I mean, just talk to some of our fifth-year chemists. They are absolutely amazing. And this process of really thinking about how we are teaching experimental design, how we are teaching technical competence. As someone who reviews a lot of university chemistry departments from an education point of view, we are doing an outstanding job. Okay, I'm back as me now. Yeah, it's not bad, it's fine. Yeah, it's all right, yeah. All right, so obviously none of my colleagues need to read this because we have amazing labs. But if you know people in other institutions who are jealous, this book is coming out whenever I last promised it, but as soon as I get a little bit of time to finish it, this book should be coming out next year. Right, so So as Dave mentioned, I'm contractually obliged to tell you something about myself. So in this second part, which I'll try and keep mercifully brief, I'll tell you a little bit about myself. So the first thing that everybody, I think, hopefully should know about me is that I'm Irish. So whatever about those YouTube comments, don't believe them. I am from Ireland. I'm from a small village called Enniskerry, which is just in the north of County Wicklow, itself just south of Dublin. So a very beautiful part of the world. Wicklow is called the Garden of Ireland for good reason. As you can see, it's very pretty. So this whole central area of Wicklow here is mountainous, and then lowlands run into the sea and to Dublin. We just live in that region. It's a very, very pretty part of the world. And Enniskerry is famous for two reasons. The first is it's home to Parascourt, which is essentially Ireland's Chatsworth, a very famous estate, very beautiful gardens. And the village itself, which is the estate village of Parascourt, is famous for retaining its 19th century character. It sort of has very well-preserved 19th century character. And some say very well-preserved 19th century characters, but I'll tell you about my family later. So that's, and I'm an historian, a part-time historian. Some wags would say full-time historian. I write a lot about history and love history and social history, how people lived, especially in the what's called the long 18th century, or the period of Georges 1, 2, 3, and 4. So I've written various books and things. I've shown a few here. So what are inside these books? Well, I'll just show you an example. So this is a book that really, if we have to understand the lives of everyday people, their stories aren't going to be in the big sort of general textbooks. We need to go to archives and surface things that will give us insight into the lives of these people. So this is an example archive, which is the workmen's account books for Parascourt, which I mentioned, from 1855. And you can see here number 2 and number 3. This is our family, my ancestors. And this tells you what they're doing every day of their lives for 6 days a week for pretty much every week of the year, maybe 2 days off for Christmas. And a lot of what they do is something called drawing stones, which I think means taking stones up out of the earth and sort of casting them aside so the horse and plough can get through. And I thought, that's a bit grim, doesn't sound like a great existence. And then I thought, if somebody in 150 years' time looks back at my diary and wonders why is this person at committee meetings all the time, maybe it'll be the equivalent of drawing stones. The second book is about how an education infrastructure was built in Ireland before the national school system was set up. So essentially how we went from this map, which was at the time of the penal laws in Ireland, to this map, where there were many more schoolhouses. And it was just really trying to surface political forces and religious and cultural forces as to where money was coming from, essentially, to build schoolhouses. So it's obviously historically interesting, obviously. But I think there are modern lessons here for social justice. We are in the UK where 4 million children live in poverty. In higher education, we do have a remit, obviously, to think about widening participation, and this school, I think, leads the way in that. Fantastic emphasis and strategic priority here in terms of widening participation. So a lot of what I got from this really feeds my desire and to try and think about accessibility to education. And finally, obviously, this booklet really, will be of interest to everybody. I mean, how could you not want to read this book? But particular interest to heads of college and heads of school, because if you were a parish priest in the 19th century in Ireland, you had to do two things. The first was convince the masses that you were preaching the gospel and you were correct. And the second was to be fantastic at fundraising for infrastructure projects. So this book is cram-packed full of great ideas on how to raise money for infrastructure projects. So if anybody has a horse going spare, please let Dave or Colin know. Okay, so I was a child, and now I'm an adult. And these are my siblings here. So this photo is famous in our family for reasons where we all look like little sort of weirdos. The good thing about this is that I look the least weird, so that's the best thing. So as a child, I suppose our parents encouraged us to read and find out about things and be outdoors. So I sort of grew up just being interested in finding out about things and drifted into science and interested in science. And studied chemistry and physics at the end of my school years. Didn't really know what I wanted to do. Chemistry at the time really just seemed like making up lots of solution concentrations. I didn't really understand what chemistry could offer. I mean, I've seen the light now, obviously. But when I went to so I had a canoe instructor. I was a very keen canoeist, and my canoe instructor was a geophysicist, and he would talk about geophysics and what that was. I was just, this is amazing. I want to be a geophysicist. So I went to university and dropped chemistry, and took up geology and physics and maths. And after a week of geology, actually after 3 hours of geology, looking at a rock for 3 hours, chemistry was the subject for me. and did the usual academic path of I became a photochemist. So John Kelly was my PhD supervisor. Many of you will know John, a fantastic photochemist and general academic. Trinity in Dublin. In Ireland, wearing this gown is perfectly normal. But when I go to graduation ceremonies here at Edinburgh, I mean, people, other professors literally come up to me and go, as if to say, where did this beast come from? So it's a little bit too vibrant for Edinburgh. So PhD in organic photochemistry, moved on to inorganic photochemistry because it just absorbed light better, and started my own independent program then in 2004 when I was appointed as an academic. And we were essentially looking at materials that absorb light very well and decomposed, used that energy from that light to decompose materials on the surface, so essentially self-cleaning surfaces. It was fantastic work. We had 4 PhD students together, myself and Suresh Pillai, who was an amazing surface scientist. So everything's going fantastic. I should be standing here in front of you as an inorganic photochemist, telling the virtues of photocatalysis. And then I met what can be described as these 2 disruptive forces, Claire and Christine. I had just started in Dublin, and they had come back from a conference, and they were talking about 2 things that really interest me: the architecture of the city they were in and the volume of food at the conference. And I had to find out what this conference is about. And it turned out to be about something called chemistry education. And I honestly couldn't believe there was such a thing, but I soon found out that there's a very rich literature in this, a lot of scholarship in this area, and immersed in it over the years. And indeed, Claire and I and Christine did a lot of work together. You'll see obviously here practical skills. This obviously feeds into my ongoing interest. And this paper became quite influential, actually, even though we didn't think it at the time. And we did a lot of work and immersed in a community of chemistry education people in Ireland and the UK and abroad. So these 3 people, Claire you've already met. Stuart was somebody who had a big influence on me in terms of lab education. He was based in the Open University. And Tina Overton, who is here, is a mentor for many people in the chemistry education community. So much so that last year we were able to celebrate Tina's contribution. She'll be delighted that I've brought up a slide to chemistry education by publishing this festschrift. So this is 60 or 70 authors writing about how to teach chemistry along themes particularly aligned to Tina's interests, careers, employability, and so on. So we launched this in Prato, which is just north of Florence, last year. So it's a beautiful city with lots of food. All right, and my own contribution to this community, I suppose, are to try and keep upping the skills and upping the awareness about education research methods. So I run this conference this is a cheap plug, by the way. I run this conference every year. It's in Edinburgh. And really the idea is to fly in experts from around the world and get them to share their insight into education research methods. So I'm at Dublin doing lots of nice work. Won the RSE award, as Dave mentioned, which was presented by local here, Leslie Ellerleys. Everything's going fantastic. I missed the IT terribly, but one issue there was it was a teaching-focused institution. So that meant 18 hours every week of semester for both semesters. So I'll just let that number settle into my colleagues' brains for a moment. So this is a huge teaching commitment, obviously, so it was impossible to really sort of meaningfully engage. So when I got contacted by yet another person on this plaque to come over for a chat, I did so, and the opportunity was fantastic, and I was very delighted, really delighted to join the department in 2015. All right, so we're nearly there. The wine is brewing. So, any questions? Right, so this last part, I suppose I want to move away. So the first part of the talk is very much about information processing and information management, which is great. I think it's very important to think about that, but in a way it reduces students to these sort of boxes that we shove information into and they process it. But of course, when we talk to students, and what I'm trying to get across using this Yeats picture here, Yeats is very famous for drawing images that, at first glance, it just looks like a blur, but as you look at it and study it closer, you start to see individual characteristics and individual people coming through. And that's what it's like. That's one of the most rewarding things of being academic when you work with students. You get this sense of individuality in every single student. And how we then treat students and talk to students and work with students is very much based on this sense of individuality. And as a good example for this, one of the nice parts of my job is I supervise final year bachelor students. who wish to do science education placement, so they do chemistry education projects, and just look at the variety. So they choose and design their own projects. I mean, we look at the variety of these. You don't have to read between the lines too much to find out some messages. So we're seeing here students talking a lot about chemistry in context, wanting to see and apply and show the power and value of chemistry to real-life issues and real-life problems, or looking at issues around transition from one education system to another, or one country to another, or looking at teaching resources and improving the teaching quality of chemistry. So these are amazing students, and they will be delighted, absolutely delighted that I've told you that you can go to their presentations tomorrow at 10 o'clock in T100, which is just down the hall. Okay, so what I want to talk about here is how do we represent chemistry, or indeed how do we represent chemists? So on my title slide, I used the image on the top, which is a very obvious image to use for me. I'm interested in history. The talk is mostly about lab education. Here's an old chemistry lab. But of course, I could have used the image on the bottom left or the image on the bottom right. I could have made a conscious choice about these, or it could have just been a random thing. And the image I choose will very much resonate with different people very differently, because different people will associate with these images. So the use of images and the consideration of how we represent chemistry is very powerful. And this is the basis of a project that we are doing, looking at chemistry textbooks. Because for school children especially the textbook really defines the discipline. So whatever is in a textbook, this is saying a lot about what's in a discipline. So this is a project with Claire Murray, who's a scientist at Diamond Light Source, and again, two of our undergraduate students who are now fifth years. And these two students are amazing. They've set up the Edinburgh University Women in STEM Society. They were Equate Scotland champions. They're really fantastic advocates. And we wanted to answer a very simple question, which was how are women and men represented in school textbooks? So we chose four textbooks. So we chose the Irish Leaving Cert, the A-level for England, Wales and Northern Ireland, and two Scottish Highers. We chose two Scottish Highers because we couldn't find out from chemistry teachers which was the most popular textbook. So we chose both of them. And the first thing we looked at was the number of times women and men were named in these textbooks. And you can see across all four textbooks there is a predominance towards naming men. And what this looks like in practice is, for example, it's the Irish textbook. These are all the men named. The Irish curriculum is unusual in that it specifies certain scientists' names that must be mentioned, and they're in italic, but you can see about half of them aren't specified. So the author here has made a choice, unconscious or conscious, to name a load of additional men. And these are very sensible, logical names, nothing to say anything about that. All my colleagues will be able to look at these names and go, yeah, I know why that person is mentioned, I know the bit of chemistry that relates to. But the problem is when you compare that with the number of times women are named and the contribution that women have made to chemistry, it's obviously completely underrepresented. So Marie Curie is the sole name here, and of course the sole name generally. And then we moved on to looking at images and the images used in textbooks. And here, the first thing we did was a very simple count. So here we counted all the images of men and women in textbooks, excluding images of both. So for example, Marie Curie does appear in textbooks, but only with her husband, Pierre. She doesn't appear on her own. And found that there was a predominance towards showing images of men in textbooks. Unfortunately, the Irish case is very extreme. But there are, for example, one of the Scottish Highers doesn't have any women pictured at all in the textbook, and the other Scottish Highers has 4 times as many men. And part of this is what we call the chemistry history factor, the slide I showed previously, where there are lots of names associated with chemistry history that are just, for whatever reason, that they are there. We sort of accepted. So we took out all of the famous people from the images, and we said, okay, if we just look at the unknown people, the stock images of scientists doing something, or member of the public wearing sun cream or wearing a Kevlar vest or something, showing the application of chemistry in everyday life, what's the count there? And found again that there was a predominance towards showing men, and the representation of men in these textbooks was much higher than that of women. And then we looked at scientists. So we distinguished these, what we call unknown photos, as scientists, in other words, stock images of people in the lab, and others, which is just people applying chemistry in everyday settings, and found that apart from the English textbook example, there were more scientists shown as men than as women. And finally, the kicker really is that UNESCO have a project for textbook analysis. This is a global project where they're analysing textbooks for these reasons all around the world, and they have categorizations. And they we analysed these unknown non-scientists and put them into categories. And the photos tended to show men, such as somebody wearing the Kevlar vest tended to be a policeman in an occupational activity. The person wearing suncream tended to be a male cricket player, showing the application of suncream. So men tended to be in occupational and sport activities, and women tended to be in domestic and buying activities. So overall, it's not a pleasant picture. I mean, I'm meant to be this cold-hearted education researcher, but it's 2020. We really need to do something about this. So what are we doing? Well, we are speaking at teacher conferences. We are raising this with teachers and raising awareness of this. We are writing to publishers and telling them, do you know what's in your textbooks? We are now have data that we can inform curriculum design. So as soon as curriculum calls for comments on curriculum designs come out, we have data that we can inform. And the RSC have been funding this work and are now continuing to fund it for a second phase. And this second phase will be looking at, okay, well, let's look at what's in the chemistry curriculum. What woman would you choose? What woman would you associate? And making up resources so that teachers would have additional resources that they can use in practice. So you can follow all that on this website. A related project is looking at the broader issue of what's on the web. And there's a project called Wiki Women in Red. And on Wikipedia, if there's a red link, it means it's a page that should be there but isn't. So Women in Red means links to pages about women that should be there but aren't. And the Women in Red project essentially counts the number of biographies of women compared to the number of men, and clearly there's a large discrepancy. So every year for Ada Lovelace Day, we had this project where we tried to have events where we could crowdsource the writing of Wikipedia pages about women. And this is Ewan McAndrew, who's the Wikimedian in residence here at Edinburgh, and Melissa and Anne-Marie Scott, who are both from Learning, Teaching and Web Services. And obviously going back to my history, I dug out of the archives of what is now the Royal Society of Chemistry. And this is a letter that 19 women wrote in 1904, so Marie Curie had just got the Nobel Prize, saying that they should be eligible to become fellows of the Royal Society, fellows of the Chemical Society, which is now the Royal Society of Chemistry. And they set out a very logical letter about papers that they had published in society journals, the science that they were doing, and saying that, there's no difference here. And the very fact of being a woman academic chemist at the turn of the century itself was notable. So these names and this work fulfilled all the criteria for Wikipedia pages. So we had events where we were able to say, okay, so let's create the page, and then let's create 19 Women in Red links for these people, and then we crowdsourced information from a large group of people, and we're able to create 19 blue links for all of these people. So this project kind of rolls on as we find more and more candidates that we can create pages for. And the last bit is just to say that obviously issues around identity and belonging obviously extend much further than gender. And the Royal Society of Chemistry have atoned for their 1904 sins, and have done a huge amount of work in this area. So they published several reports, one of which explores representation in STEM and in chemistry, and considering particularly issues of disability, and have written a pretty stark statement. I mean, we're even worse than the physicists, which is hi Ross, which is saying something. Physicists are great, but this sense that who is allowed to do chemistry is really a message that is not getting out very well. So they've come up with this statement, which is really a call to arms, and they fund projects in trying to address this. So I've been thinking around this for a long time. I share good practice of what we can do and so on. That's relatively easy. But we've moved on now to a new sort of level of project where we ask students to declare if they have a disability and say, what was useful to you in your teaching when you were a chemistry student? And for me, this is fantastic, because I hear these students talk about lots of things that my colleagues are doing that were very empowering for them as learners. And what we're trying to do in this project is sort of recognize what is going on, surface that and share it, so that people are aware of what they're doing, and then other people can see things that perhaps don't have a large workload associated with it, can perhaps start to do that as well. So it's trying to move away from the deficit model of trying to say, oh, I have to do this extra little bit for student X in my class, and just start to think about what's called universal design for learning, which is essentially designing our learning processes so that they're accessible to a much broader range of people. So that's another ongoing project. So just what I'm trying to do in this part really is to move on from this sort of USB memory key going into student brain and recognizing that for our students and for our learners, yes, motivation and interest and passion about chemistry is a huge part of who they are, but also there's another very big part of who they are, issues I've mentioned and many more, that really define their learning. And for us as educators, and one of the great things about this department is that we are very, I think, tuned into this because we've got a very good senior personal tutor who makes sure we are, but this has to be part of the dialogue that we have with students. Okay, so those waiting for wine will be glad to hear we're now towards the end. So I just want to say a few thank yous. I've mentioned this sort of chemistry education village, this network. They've been very powerful to me in terms of helping me immerse in this discipline. So I've listed as many people as I can think of here, but I know I've already forgotten people, so thank you to those. Moving mid-career isn't easy, so I do really gratefully acknowledge the people here at Edinburgh in different disciplines who welcomed me in. So I haven't included colleagues in science and education specifically, but they're under this umbrella. And I haven't mentioned, but should acknowledge, that I'm also involved in other PhD student work led by these other colleagues in different parts of the university. And that's just such an amazing thing, an amazing opportunity for me to learn so much from those experts. So thank you to those. Thank you to my colleagues in the department. So the curriculum transformation I mentioned at the start is obviously much bigger than me. And this is a huge project that many of us, all of us, have been involved in for the last few years. And the fact that the school is willing to take on and really lead the way in terms of thinking about how we teach chemistry, it means it's a great place for someone like me to work. Hidden in here are some technicians. So, of course, when I go into the lab and go, let's do it this way, the technician has to be able to think about how this is actually going to work in practice. And we have a fantastic team of teaching technicians here who make that happen. In the last part of the talk, I mentioned things around inclusion and diversity, and that's obviously means there are often difficult conversations. But this is really a great school, again, thinking about taking the leadership in that, and making very proactive decisions on that, and real actions that make a difference. So thank you to the leadership in the school, Colin and Alison, for facilitating that. I would like to thank, obviously, everybody's an academic knows it's a bit of a roller coaster, so thank you, oops, not those people. Thank you to all of these people, friends and family and so on. I will just mention my family here. Thank you very much to them. Shuttle Scots are here. So it's quite I learned it's quite hard to make friends when you're in your late 30s, so Shuttle Scots have been our saviour, so thank you very much. They're just here for the wine, but you know, you've earned it, and it's coming, so thank you very much to them. And finally, I'll just thank Matthew. So many of you know Matthew. He's my partner. Here we are having lots of fun. He's been a real guide on the side here in all of this process and been very supportive of me. Thank you to Steiner and to Sharon for organising all this. A huge task, I really appreciate it. And thank you very much.
Well, thank you, Michael, for an absolutely amazing lecture. That was really eye-opening, and I think it's I hope it's caused lots of colleagues to really think about what they're doing, realise actually the huge impact that you're making. So, just a few words to say about Michael. I mean, he's clearly, as you can see, an outstanding lecturer. He cares passionately about our students, their learning, their welfare, and you can see that through the design and delivery of these innovative methods of teaching, he really is making a huge impact. And I think he's very modest about some of the changes that have taken place. So I remember I was director of teaching a while ago, and every staff-student liaison committee, we would get the same old thing. Oh, it was the labs. It was the labs, and I used to dread. Here we go. And I think Phil Bailey, you also experienced that. We used to dread the feedback from particularly the third-year labs. And since Michael sort of took control of those labs, suddenly that's no longer on the agenda, and that's a real triumph. I think, as you can see, Michael's been promoting initiatives for addressing the diverse nature of our students. I really love your point there about these students are individuals. That image is really very, very powerful, and you can clearly see that Michael's passionate about this, and that positive impact on the school has been really very, very, very impressive. Now, I think particularly in his role as director of teaching, Michael's very persuasive. He doesn't do it by shouting and stomping around. He does it by, well, he'll suddenly appear in your office and have a discussion with you, and by the end of it, you realise actually you've agreed with him, that quiet influence of colleagues is really exceptionally powerful. And part of that, I think, I hope you've seen today, is his credibility as a research leader in chemistry education. And I think he will give you the data, right? And we as scientists, we're very impressed by data. That's what guides us. And if you want to convince a chemistry academic that to change the way they do things, then give them the data in a way that they can understand. And doing that, I think he succeeds in challenging our prejudices and preconceived ideas. Many of us have been chemists for 30 plus years of our lives, and we know the right way to do things. But of course, times change. We have lots of preconceived ideas, stereotypes. Michael is challenging that, but he does it very gently. I think you perhaps got a little taste of it here, but I've been really struck by Michael's national and international reputation, and that came through actually. And Dave will know about this when we look at the referees' comments from the very painful promotions process. We have to have 4, 5, 6 referees, some of whom are international. And some of the comments that were simply just glowing, and clearly Michael's international reputation in the field was absolutely outstanding. But I also get that I'm a member of the Heads of Chemistry UK, and I get to meet other heads of chemistry 2 or 3 times a year. And they say, "Oh, Michael, you've got that Michael Seery. He's fantastic, right?" And I hear that. Well, he is. Clearly, he is. But that's very reassuring, and makes me feel good that we've got one of the world's best chemistry educators in our school, and he's working with us. And I think that's recognised by his role in the Education Division Council of RSC and the numerous awards and the publications. There is a man there who's really influencing the wider chemistry agenda. We did have a little bit of a chuckle about when he got the award of the RSC Inspirational Member. At least some of my colleagues chuckled about that. But I think that is richly deserved. Michael is inspirational, and I think that comes through today. What Michael hasn't mentioned that he's very partial to a little tipple of gin, and the infamous gin nights organised by one of our colleagues, Professor Carol Morrison. Michael apparently is a stalwart of that, and is usually the man who's holding his own. And great evidence was also shown at the last year's chemistry ball. So he claimed earlier in the evening that 11:30 he was going to go home, leave at 11:30. But then 11:30 came, and he then persuaded all of the staff who were still there that we should all go on to the Why Not nightclub. I can't even remember. And sure enough, there he was. He was boogieing away all night, the last man standing. So he got huge kudos from the students. There are other stories from the ball, but I won't. You can ask him about that over a glass of wine. And then finally, a little personal reflection. So Michael is a fantastic colleague. He gives me great support as a head of school, knowing that I've got a director of teaching who completely gets it and is in control. I don't have to worry about the teaching side of things. He always gives me very thoughtful, considered answers, and with very high degree of emotional intelligence. There's It's rare that he gets angry. He gets angry occasionally, but he's usually very, very calm and collected and is able to solve problems. Exactly what you want as a trusted colleague. So I think hopefully you've got a taste for what Michael is doing. I think it's putting this school of chemistry at the forefront of changing the way we teach chemistry. And Michael is very, very clearly leading that. So I'd like you to join me in thanking Michael for an absolutely fantastic inaugural lecture, and wish him very well for the rest of hopefully the rest of his career in the school. Thank you, Michael. So now we can adjourn into the social space for some well-deserved wine and some cannabis. Fantastic.